Again, another topic that hopefully might take your mind back to some of your earlier studies in maths is the study of rational or irrational numbers. So the subset of real numbers that I can write as an integer divided by an integer is the set of rational numbers. So for example, 0.4 would be rational. I could write that as 4/10, 2/5, 40/100. There's not necessarily a unique way of writing them, but it can be written in this form. Famously, the exact value of pi is not rational. People might write it approximately 22/7. That's true, approximately, but there is no integer divided by another integer form that will give the exact value of pi. So, revising what we saw previously, that this uppercase R is the set of all real numbers and Z is the set of all integers, Q is the set of all rational numbers. And I think a fairly easy definition, if a number is not rational, then it is irrational. There's a commonly told story in the history of mathematics, may or may not be true, but proof of the existence of irrational numbers is often credited to a student of Pythagoras. Now, Pythagoras himself is said to have believed strongly and believed wrongly that all numbers were rational. That is, for example, that you could find two integers, one divided by the other would give you, for example, the value of pi. And Hippasus was Pythagoras' student, and Pythagoras himself. That picture is actually from Raphael's The School of Athens, which also provided a picture for two Guns N' Roses album covers. Anyway, so there's Pythagoras and there's his student, and it is said that Pythagoras and his student disagreed so strongly that Pythagoras had his student killed. So rather than convincing him, he sent him out on a raft to drown. So the story goes. It's often debated or disputed. Probably isn't true, but just be thankful nobody teaching the subject will kill you whether or not you disagree with them. That is a promise. Before we go into the final proof for this section, we just need one further definition when it comes to rational numbers. Now, a rational number is just one that can be written as an integer divided by an integer, but there is no unique way of doing that. That 10/30ths is the same as 2/6. 2/6 is the same as 1/3. Similarly, it's 100 300ths. But there is a simplest form, and the simplest form is when I've made sure that the top of the fraction, the numerator, and the bottom of the fraction, the denominator, have greatest common divisor of 1. So 10/30ths isn't the simplest form because, for example, I can divide top and bottom by 5 and get down to 2/6. 2/6 isn't the simplest form, so I can divide top and bottom by 2 and get down to 1/3. 1/3 then is the simplest form. So, with a bit more notation, we define the simplest form of the rational number, n equals a over b, to be such that the greatest common divisor of a and b is 1. So we can show by contradiction, prove by contradiction, that the square root of 2 is irrational. So, like all proofs by contradiction, we actually start by assuming that the opposite of what I believe to be true, that I want to prove to be true, we believe the opposite of that is true. So to show that root 2 is irrational, I start by saying, no, I'm going to assume that root 2 is rational and that there are integers a and b, such that a divided by b is equal to the square root of 2. And this is not just any a and b. I will assume that that is the simplest form of the rational number square root of 2. Well, if the square root of 2 is a over b, then a squared is equal to 2b squared. Well, if a squared is 2b squared, then 2 times an integer must be even, so a squared is even. We've already seen that if a squared is even, a must be even. And if a is even, there exists another integer c such that a is twice as big as c. A equals 2c. But if a equals 2c, then a squared equals 2c all squared, which is twice b squared. It's 4c squared, which is 2 lots of b squared. So that also tells us that 2c squared has to be b squared. That also tells us that square root of 2 is b over c. But I assumed that the square root of 2 was a over b in its simplest form, but I've managed to get it simplified further, which contradicts the original assumption that I started with the square root of 2 as a over b in the simplest form. So if I assume I've got the simplest form, I show that I haven't got the simplest form, which is a contradiction. So the part which is wrong is that square root of 2 being rational in the first place. So we've proven that the square root of 2 is irrational. Now, I can prove directly, not by contradiction, but I can prove directly that between any two different rational numbers, there is another rational number. So this shows that there will be infinitely many rational numbers and infinitely many rational numbers between any two rational numbers. So I'm going to assume that I've got two different rational numbers a and b, such that a is less than b. They're both rational, so I'll call a p over q and b r over s, where p, q, r and s are all integers. Now if I work out the average, the midpoint of a and b, that's the average of p over q and r over s. So it's p over 2q plus r over 2s, which I can write as ps plus qr over 2qs, if I put it all over a common denominator, and that itself is rational. So any two rational numbers will have a point in the middle of them, which is also a rational number. So of course, if I then pick that midpoint and either endpoint, there's another one in the middle of that, and another one in the middle of that, and another one in the middle of that. That it doesn't matter how close A is to B, there will always be an infinite number of rational numbers between my two endpoints.